Hi, everybody. This is Mr. Fowley, and welcome to 5.2. Yay! So now we are going to look at basically table analysis on this all the time. So we're going to start with rate laws. Rate laws will always look like this. Rate equals some constant K. K is the rate constant, and its units can change. And rate is going to be in molarity per time. It's usually molarities per second. It could be molarity per minute or molarity per hour, but it's molarity per time. X, Y, and Z are in brackets, right? And they're in molarity. Remember, the brackets mean molarity. Only aqueous and gases are going to be listed here because their molarities change. Solids and liquids do not have concentrations that change, so they're not listed there. A, B, and C are exponents describing the effect of concentration of that reactant on the rate. Options for A, B, and C are 0, first and second order. That's only for AP chemistry. There's other ones, but really for us, there's only going to be 0, first and second, and they are not the coefficients. We are often tricked into thinking they are, but they are not the coefficients. Okay, so let's take a look. Oops. So if I have A yields products, that's going to be unimolecular. Okay, so that means one thing is just going to hit. All right, so rate equals Ka to the first. A plus A yields products, that's bimolecular. It takes two specifically A's to do that. A plus B yields products, that's bimolecular. It takes two molecules to hit. Termolecular would be 3, and we won't go any higher than that. Higher than that does exist, but we're not going to go any higher than that. This is called molecularity. Molecularity is essentially how many particles have to collide with enough energy in the correct orientation. Second order has 2 particles collide with enough energy and the right orientation. So if I have first order, that means I can just hit a wall. And one of them is good enough. And then it splits off into okay. Second and third order are much harder, then they're slower and less frequent to encounter. That's disappointing. All right. So rate is, so this is rate, change in concentration over change in time. And rate is going to equal Ka to the M. And we use all kinds of different, it's annoying how they use all kinds of different exponents here, but that's going to be the exponent that we're looking at. Okay. So there are 3 of them. Remember, there's 3 that we talked about. We have 0 order. Oops. We have 0 order, first order, and second order. See, 0, 1, 2. And if it's 0 order, that means it has to be there, but it really has no effect on the rate. Okay, so I look at that like if you're playing a sport, you need to have referees. Referees don't make the game go faster. They don't do anything like that, but they have to be there. As long as you have 1, you can play a game. If you have 2 or 3 or 4, that's fine, but you have to have 1 to play a game. Okay, so on this, the integrated rate law, so basically you need to know that this is the equation that you have to deal with for each one. So if it's 0 order, again, would be A equals negative KT plus A naught. If it's first order, notice the biggest difference here is the ln. ln A equals negative KT plus ln A naught. And look how this is Y equals MX plus B. Y equals MX plus B. Okay? So you can see on each one, this is 1 over A equals KT plus 1 over A naught. So Y equals MX plus B. Whoops, my writing's not coming through here. So notice how X is going to be the time. So when I'm going to graph these, and I will graph these, notice how the Y is A and the X-axis is T. The Y is ln A and the X-axis is T. The Y is 1 over A and the X-axis is T. And you can figure out where those go for the rest of it, okay? Half-life, it is worth memorizing. Now realize with math, you can figure out any of these half-lives, okay? So the way you find a half-life is you could call this 1, the original amount 1, and the amount at time t 0.5, right? And then plug it in. So if you know K, you can solve for that. How would I get K? I would use the slope of the line, okay? It is worth memorizing that the slope of first order is ln2 over K. ln2 is 0.693, okay? The order with respect to A is the exponent on A alone. So if it asks you, what's the order with respect to A? You are going to say the order just for A. The order with respect to B is going to be just the exponent on B alone. The order for the entire reaction is the sum add up for each part. So that way, if you see a question like, I don't know what that's asking, that's it. Units for K, you can do math to figure this out. So if you remember, I tend to do the math on this. Rate is most typically molarity per second. So molarity per second equals rate times K, and then molarity to the 0. Anything to the 0 power also loses its unit. It becomes 1. Even the unit becomes 1, so there's no unit. So that's why K is molarity per second, right? If I'm looking at the second one, it would be molarity per second equals K times molarity. Well, see, my molarities will cancel out. I'm going to get 1 over time. I do know there's a handful of people that do like to memorize things instead of math them out, which is just fine and dandy. Also be aware that sometimes the units for K could be molarity to the -1, seconds to the -1. Remember how if it's on the denominator, that's shown that way quite a bit. All right, let's keep going. Determining the order by experiment, and this is where we use tables. All right, so here's my reaction. NH4 positive aqueous, NO2 negative aqueous yields N2 gas plus H2O liquid. This is not, the liquid is not going to show up in it because its concentration doesn't change. Okay, so no solids nor liquids because molarity is constant. Okay, so let's find order with respect to NH4 positive. So what I'm going to do is I'm going to look for a time when my concentration of NH4 is going to change, right? So notice here it doubles, but here it's times 1, so there's no change in it, okay? Does that make sense? So we want to see where NH4 doubles. Use experiment 2 and 3, so NH2 is constant. As NH4 doubles, the rate doubles. Hey, that's what I said. So the rate here doubles. 2 to what power equals 2? So the order is 1. So that means if I did this, I would say rate equals K NH4 to the first. Okay? Find order with respect to NH2 negative using experiment 1 and 2. So notice how these are the same, times 1. Here, this is times 2. And here, the rate is times 2, right? So it's also 1. So that means NH2 negative is also first order, okay? So it says find the overall order. 1 plus 1 is 2, so it's second order. Write the rate law, and we kind of did that already up here. Find K at this temperature. Okay, the only thing that changes is K, and that's the temperature. So let's look at experiment number 1. So we're going to substitute into the rate law. We found our rate law. So we had the rate from the very top part up here. So the rate, and I just like to use the first experiment. The rate is 1.35 times 10 to the negative 7. This is NH4 positive. This is NH2 negative. I just plugged it in. Substitute the rate value from the table, K, 0.1 to the 1, 0.005 to the 1. Do the math. And K equals 2.7 E negative 4, molarity negative 1 seconds negative 1. Note, rate is always molarities per second, and brackets means molarity. So watch your exponents. Let's do another. Yeah, I like to do more. These are annoying in the beginning, but we'll get good at them. So looking right here, this doubles, and these other ones are constant. So what happens here? This is times 2. So that means I'm going to do rate equals K times bro 3 negative, Br negative, H positive. Okay, so notice these are the same. If these are the same, it's first order. Okay, let's look at this next one. So right here, this is times 2. Notice these are times 1, and these are, come on, let me draw. And this is times 1, okay? So when this is times 2, this is also, this is also times 2. Okay, you can throw it in your calculator if you want to, but I can tell that 16 times 2 is 32. So that means that's also first order for Br negative. All right, so now we got to find H positive. Okay, so we need one more. All the other ones are the same. Clear this out so I can have it a little cleaner. So if I use this one, this doubles, but these all double, so that's no good. This one doubles, but this one still doubles. But here, if I do from here to here to here, the only one that doubles is H positive. Okay? So when H positive doubles, notice that this one is times 4. 2 to what power equals 4? Well, that's 2. That's squared. Find the rate law, and solve for K with units. So notice how this is moles per liter per second. I like to make that molarity per second, equals K times molarity, molarity, molarity squared. Molarity and molarity and molarity squared down to the 4th, okay? So I'm going to cancel these out. I'm going to have K equals 1 over molarity cubed seconds, which could also be K equals molarity to the -3rd seconds to the -1. Okay, so now I guess I have to solve for K. So I'm going to use my first equation. I use the first one just so I don't mess it up, okay? So I have the rate, using this right here, I'm going to write it right underneath it. My rate is 8e-4 equals K, which is what I'm solving for. Bro 3 negative is 0.1 to the 1, 0.1 to the 1, 0.1 to the 2. So 8e-4 divided by 0.1 divided by 0.1 divided by 0.1 squared is 8. And then my units I found before, molarity to the -3, seconds to the -1, and up here is my rate law. All right. Find the rate law and solve for K with units. Okay, so one more. So on this one, see how this is times 4, times 1, and this is, I'm going to check to make sure. What's 16 times 4? 64. So that's times 4. So notice how 4 to what power x equals 4? That's 1. Rate law time, rate equals K, A, and it's very common to do the A's and the B's. And this is first order. Okay, so let's see the B. We have, oh no, A changes every time. How awful is this? Okay, so usually I want to have something where B will change, but A will be, is that what I did before? But A will be constant, but I don't have a way of doing that. So what I'm going to do here is I'm going to go this one because it's pretty easy. Okay, so A doubled, right? B doubled, and this is times 4. So I'm going to show you something. This is going to blow your mind. Something you learned in math in like 6th grade that you always thought was a complete waste of time is actually useful here. 16 to 64 is times 4, okay? Check this out. I'm going to factor this. The times 2 of it is because of A. So this times 2 of it must be because of B. So B 2 to the x equals 2. Did you follow that? Okay, so times 2 is because of A. We found out that A is first order. So that means I know it's going to double because of A. The other factor changes 2. So when B doubled, that doubled, and it's first order. Okay, find the rate law. Here's my rate law. Solve for K with units. So we'll go back to the first one. 0.0016 equals K, 1 to the first, 1 to the first. So K equals 0.0016. And then these are molarities. Those will cancel out. So molarity of the -1 seconds to the -1. And that's it. Not too bad. Toodles.